The last major issue that we have to address is this idea of activity as it relates to chemical potentials. And we've seen that the chemical potential is really very central to a lot of problems, particularly under conditions where temperature and pressure are constrained or at least controlled. So last class, we ended up by introducing this idea of the activity of a species in a mixture. Okay, and so we saw that in an ideal solution, let me just reiterate that. So for an ideal solution, right, and so we're talking about a condensed phase and in particular liquids for the moment, but this applies to any condensed phase or any non-ideal phase. We saw that the chemical potential for an ideal solution, which is a mixture of various liquids, and the ideality means that the interactions are all equivalent between species. We have this form of the chemical potential for a species I in that mixture. Okay, so the chemical potential really is a mixture property. It belongs to a particular species, but it is really relevant when you have a mixture. The chemical potential of a pure species is really just a molar Gibbs free energy at conditions of constant temperature and pressure. Okay, so when you have a mixture of liquids in the condensed phase, you have a solution. And this actually also applies to cases where you have a solid in equilibrium with a liquid. So again, you can have cases where you have something a chemical reaction you may perform in solution, and then something precipitates out as a solid. And so in that case, chemical potentials also are relevant. Okay, chemical potentials are always relevant. So this is the form of the ideal solution chemical potential of a species I, and you see that it has some initial part that's a reference state, and then some other part that takes it from the reference state to the final state in which the solution or that mixture exists or you're interested in. And in this case, the formulation involves the mole fraction of species I, x sub I. And so x sub I is unitless, right? And we know that the log function actually can also be thought of as representing a difference. So if you, as we've seen in this class, remember, when we get things like log of p sub I over p sub I naught in some reference state, we immediately recognize that that log is representing the difference between something in that reference state and the current or final state of interest. Okay? So in this case, we just have mole fractions. And it seems that if we were to say that, okay, we have the log of x sub I divided by x in some system, it seems that that x sub I is equal to 1 in the denominator. And that's consistent with the fact that in this representation of the ideal solution chemical potential, the reference state is a pure I state. It's just pure species I at the saturation conditions of the pressure and temperature at which you're looking at the mixture. And so we see here that this term really is still a ratio, but since we're talking about a reference state that is a pure state, the mole fraction is just 1. And so that log takes care of the difference between that. The other way to think about this log, right, is just by bringing over the mu I superscript saturation to the left, and you'll see that then that just becomes a difference in the chemical potentials. If I were to bring this guy over to this side of the equal sign, we see that we get a difference in chemical potentials, and that difference is given by RT log x sub I. And we can say that it's x sub I over x sub I in some reference state or the initial state. Okay, so really logs are another way to interpret logs through their arguments is as differences in functions between two different states. Okay, and we know that mu is g, so it's a state function, and so it all fits nicely. That all we need is the log of a ratio to get the difference. So this was the form of the chemical potential of a species I in an ideal solution, where you have some reference state plus the difference to go from the reference state to whatever state is of interest. So we could generalize this for non-ideal systems, non-ideal solutions, okay? And the way we did that was to add a difference now. So if we, you can interpret this again in many different ways. In this expression, what we've done is just add a term that's RT log gamma sub I, and this thing gamma sub I is the activity coefficient of species I in this mixture, in this non-ideal solution. And so we see here that that is a term that adds in addition to the ideal solution part. So this is the ideal solution part, as you remember from above, is just as a reference state, in this case, the saturation state plus RT log X sub I. And now we're just going to tack on the term, which we can derive rigorously, but I haven't. I've just given you the final result, is that RT log gamma I is this difference between the ideal case and the non-ideal case. Okay. So if you were to take, and then we can actually lump the X sub I and the gamma sub I terms together in the log, and we obtain this expression, okay, where we see that the chemical potential of a species I in a non-ideal mixture is some reference state chemical potential plus RT log of the product of gamma I times X sub I. And again, we really keep in mind that there's a denominator with this X sub I, which is taken to be X equal to 1, because we've chosen a reference state where we have pure species I. Okay? And so gamma I essentially takes care of all the non-ideality of the solution. When gamma I, the activity coefficient of any species or of every species in the system, is 1, that means you have an ideal solution. Okay? And then when gamma sub I is not equal to 1, it can be greater than or less than 1, you have a non-ideal solution. Now we're departing from ideality. Okay? And so we can define this product gamma I over xi to be the activity of species I in solution. And so this is a definition. And in fact, if you want to be consistent, we can say that this is gamma I X sub I in the system of interest divided by X sub I in your reference state. And if you take the reference state to be pure I, then X sub I has to be 1. Okay. And so this is an important thing to keep in mind, this ratio. Okay. And depending on what you use for this representation of composition, whether it's mole fraction or concentration or ppm or whatever you use, gamma I will change. It would depend on that representation that you choose. Regardless, it's this ratio between the point of interest, in this case X sub I, which is the composition of ion in the system, divided by the composition in your reference state, Xi superscript 0. Okay, so is that clear to everyone? Okay. And by writing it this way, I've just assumed that X sub I superscript 0 is 1. I've taken a pure reference state. Okay, and so this thing called the activity is very important. Okay. It allows us to handle non-ideality. So finally, with the incorporation of activity, our expression for a non-ideal system, the chemical potential of a species I in a non-ideal system, becomes this last expression, and that's what we left off with last class. Okay, so again, so for a species I in a non-ideal solution, and now we can extend the solution to just be some mixture of anything. It could be vapor phases or anything like that. This applies to any kind of solution, okay? Whether it's a bunch of vapors, it's a bunch of liquids, or it's a combination, a bunch of solids. It could be a combination of solid and liquid, solid and vapor. Okay? This is very general. And so for a species in a non-ideal solution, at a particular combination of temperature and pressure, okay? And of course, we have in composition the chemical potential of that species I, which is non-ideal, at some pressure, temperature, and now we can just say composition. Because we can say composition can be in terms of mole fraction or concentration or any other, or ppm, whatever you wish. That's why I put composition in this bracket here, and I've just labeled it as composition, is going to be mu sub I in some reference state at those conditions, plus RT natural log A sub I, okay? And that A sub I is gonna, of course, be a function of pressure, temperature, and composition. Okay, and so this is our general form. Okay, so any questions on that? Okay, so let's see how this plays out. So maybe some examples of application or the relevance of A sub I, which is a function of temperature, pressure, and composition. Okay, so application or relevance. And for this, recall, for the following discussion, recall that I said that A sub I can be written as gamma I x sub I, which is really gamma I x sub I over x sub I in some reference state. Okay, so this applies to the reference state. We can, and so this is mole fraction, okay? So we can use concentration. Let's use concentration. These are mole fractions. We can actually write A sub I. We don't have to, the gamma I will change. So we can write this as, and I'll use these brackets to represent molarity. Okay, so that's the concentration of I in molarity divided by the concentration of I in molarity in the reference state. And let me see, we'll put the superscript 0 here. Okay, so we can define it either this way. They're all equivalent in terms of the meaning, the physical meaning. So the activity here is just this product of the activity coefficient gamma I of the species I times the ratio of the concentration of I in solution or in this mixture. And then I sub naught, or sorry, I superscript 0 is the concentration of I in your reference state, whatever you choose that reference state to be. Okay, and it turns out that this product is dimensionless. It's dimensionless. Gamma I is dimensionless. Okay, so everything is dimensionless, and that's why you can take the natural log of A sub I, because it's dimensionless. Okay, so as an example one, or our first example, let's go back to chemical equilibrium. Oops. Okay, in our generic form, our very abstract and generalized form of a chemical equilibrium situation is this canonical form, okay, where you have species A, B, C, and D. There's a transformation, but of course at equilibrium you solve by minimizing G at P and T specified. By minimizing G, we obtained this relationship between the standard state delta G for the reaction and the equilibrium constant, something that we call the equilibrium constant when we minimize G. And, that was this discussion where we had G as a function of the extent of reaction, remember, and we found that it could be something like this, where the minimum of G is that. And recall that G is just the sum of the mu I, N I at equilibrium, if we were talking, well, along the whole extent of reaction, but G is minimized, and then that would become dG d epsilon is 0 at equilibrium. Okay, so that's a discussion. I'm not going to go through the whole thing again. It's in the notes and everything, and in the text. So we saw that this was our chemical equilibrium, and we saw that after going through this dG d epsilon equals 0 for having equilibrium, we came up with a condition which was some of the nu I mu I is equal to 0, where I goes, of course, in the set from A, B, C, and D for this case, but it's actually all of the chemical species. And this was the criterion for chemical equilibrium, which is really just a manifestation of dGd epsilon equal to 0, okay, minimizing G, the Gibbs free energy. So this was just another way of writing minimization of G, okay, at equilibrium. Okay, and so from that we obtained, and then from that we obtained this relationship delta G naught of T is equal to minus RT natural log, okay, equilibrium. Okay, and so that was a progression here. And so when we were dealing with ideal gases, which is how we derived this, okay, we found that K, this K equilibrium, was just a product of the partial pressures divided by the reference pressure for each of the gases. Okay? But now, if we recall, now we know in general, okay, for any system, again, for any system, mu sub I at a particular temperature and pressure and composition, which I'm just now going to put in brackets, you can put in the compositions, is just equal to mu I ref plus RT natural log A sub I. Okay. Any questions so far? And so now we have this expression. If we go back to this expression right here, okay, this one right here, where we're multiplying all of the chemical potentials by the stoichiometric coefficients, right? If we were now to multiply this, and I'm going to not write the PET dependence, you can carry that through yourself. So the stoichiometric coefficient times the chemical potential of I is just going to be mu sub I times mu sub I in the reference state at whatever temperature you're interested, plus mu sub I RT natural log A sub I, okay? Which we can now write as mu sub I mu I ref of T. And this guy is going to be brought up as an exponent. So that gives us RT natural log A sub I times nu sub I. Okay, we can do that with natural logs, so logs in general. So nu sub I is just this. And now we just sum over all of the species that we have in our system. And we remember that nu sub I, the stoichiometric coefficients, have a sign. It's negative for products, and nu sub I is greater than 0 for it's negative for reactants, and it's greater than 0 for products because we're going to produce them. And we can go through the algebra here, which I'm not going to do. This is something now that you should be able to do at this point in the course, remembering that A sub I is equal to gamma I times the concentration of I over the concentration in some reference state. Okay. What this leads to for our equilibrium constant is something of this form. And I highly encourage you to go through the steps to derive this. It's not that difficult, okay? What you have is the activity coefficient of species A raised to the stoichiometric coefficient of A, gamma B to the stoichiometric coefficient of B, gamma C to C, and gamma D to D. Okay, and then we'll have all of these terms where we have the concentration of A over the concentration of A in the reference state, raised to the mu sub A. And the same thing for B. Same thing for C. And the same thing for D. Okay, and so our equilibrium constant, when we allow for the activity to be represented in terms of concentrations, which we will take to be as molarity, our equilibrium constant turns out to be this product of the activity coefficients And again, these activity coefficients are a measure of non-ideality. And then this product of concentrations raised to the stoichiometric coefficients. Okay, in this case, these stoichiometric coefficients are not absolute values. They are actually the true ones, so they can be positive or negative. Okay. And so we see here then that, remember from your previous courses where you've used concentrations in defining equilibrium constants, okay? You've never seen this thing that pre-multiplies the concentration. So there's 2 points here, okay? There's something that pre-multiplies all of these, either a product or a ratio of all of the concentrations. And what's multiplying, or pre-multiplying the concentrations is all of this non-ideality, the factors that will introduce and quantify the non-ideality of the system. You haven't seen them, or you weren't told about them, because the approximation that was made up till now is that gamma i's are 1. And so you're dealing with systems where you can treat the solution as ideal, okay? So that is what you've been sort of dealing with so far. And where systems are more or less dilute, and particularly, for instance, biological systems, acid-base kinds of systems, more or less with the systems that you're dealing with, ideality is not a bad approximation. As you've seen in your previous courses and through labs, you may see some differences when you go to extreme conditions, perhaps with high pH or low pH, extremely low pH. But for the most part, these gammas are 1. Okay. So that's the first point. Up till now, you've used the assumption or the approximation that solutions are ideal. The second point here is that when you're dealing with the concentrations, you see here that all of the concentrations which are in the numerator, which represent the actual concentrations in the system that you're dealing with at equilibrium, okay, are divided individually by reference state concentrations. And so each one of these ratios of concentrations, which is raised to a stoichiometric coefficient, is dimensionless. There are no units because all of the units cancel out. Okay, so molarity divided by molarity will leave you something that is dimensionless. Okay, so the equilibrium constant, most rigorously arrived at and derived using thermodynamic principles. And again, this expression right here, you can trace back to the first and second laws. Okay, I mean, that's all it is. It's a representation of the first and second laws. Okay, so those are the 2 points to keep in mind, that when we're dealing with any system now, okay, and so this chemical equilibrium is just one particular type of process that a system may undergo, or we may wish to consider within a system within that context of a chemical transformation, which leads to equilibrium, where you have reactants and products, but the transformation from reactant to product is not complete, so that in the end you have a mixture. Okay? And so in the most general sense, well, not most general, this is reality, things are non-ideal. And so this is what the equilibrium constant would be like once we allow for non-ideality. And so this applies to gases, this applies to solids, and this applies to liquids. And you see here that the equilibrium constant is dimensionless, as it has to be rigorously if we believe first and second laws of thermodynamics. Okay? Because this is, take your time, you can always derive this from that. Okay, so that's great. Any questions on that? So that's something I hope you will take away with you, that when we allow for non-ideality, things kind of naturally fall into place. So let's take a look at chemically, another example. Okay, so this is a general example. So let's take a look at acid-base equilibrium. And I'm just going to use water. It's very simple, but it's illustrative of what I want to get across here. It's a big and important concept. Acid-base equilibrium, and I'm just going to do the autoionization of water. Okay, so where you have water, okay? And this is something you've seen from, I know, these are in AQ, aqueous, okay? So you have this ionization. You can even think about this as H2O plus H2O goes to H3O plus in AQ plus OH minus. Okay, is that correct? Yeah. So you always get OH minus, either H plus or H3O plus. Okay. And so we don't have to, so again, we have equilibrium, right? This tells us we have equilibrium, and this is something you already know from all of your previous courses. So we have equilibrium, that means there's some equilibrium constant, right? And we know that for the system then, because all our species are either H plus, H3O plus, or H minus, we can easily write the K equilibrium. And we'll use this expression for now, okay? Let's see, is that how we want to do this? Okay, yeah, we can do that. We'll use that expression. It doesn't matter which expression you use. So the equilibrium constant, and I'll just write this as K equilibrium. You may have seen this as KW or what have you, but for this course and from what we've learned from this course, we see that this is just gamma H3O plus in the aqueous phase, gamma OH minus in the aqueous phase, because that's what we have here. We also have gamma H2O, okay, times, what are we going to have here? The concentration of H3O plus over the concentration of H3O plus in some reference state, raised to the new H3O plus. Then we have OH minus over OH minus in some reference state, raised to the new OH minus. And then finally, we have the concentration of H2O over the concentration of H2O in some reference, raised to the new H2O. So that's our equilibrium constant here.
Dr. Patel?
Yeah.
Shouldn't we also raise the activity coefficients to that? To the new?
Oh, yes. Oh, yeah. Oof. Oh, yeah, I did. Yeah, okay. So it was here. Yeah, you're right. You're right. That's correct. Who is this? Khalil? No.
Michael.
Michael, okay. You both sound very similar. Okay, thanks, Michael. You're absolutely right. So this would be the stoichiometric coefficient of H3O plus. This is the stoichiometric coefficient of OH minus. And this is that of H2O. Actually, absolutely right. Thanks for catching that. Okay. So this actually is KW or K equilibrium. Again, I have no idea who taught you what and how. So, but being self-consistent in this course, this is the equilibrium constant for the autoionization of water from pure water to H3O plus and OH minus. And you see here that this really is the most insightful way to think about this. Okay. It's obviously dimensionless, as it has to be, because thermodynamically we would have to take logs of equilibrium constant, so it has to be dimensionless. It's dimensionless because gammas are dimensionless, and now we have these ratios of concentrations. So everything is dimensionless as it has to be. Okay. The way you've been taught this is without the gammas, and so the approximations that went into that is that gamma, you're dealing with systems where things are so dilute that you don't have to worry about non-idealities. And so obviously for the pH levels that you've been dealing with, they're like 10 to the minus 7, 10 to the minus 6, right? So what this really means is that if you have a species like H0 plus or OH minus, they're so dilute that you don't have to worry about H plus water interactions. It sort of becomes like this really, really dilute species in this sea of water. And so what we call this is renormalization, meaning that we forget about the H plus water interactions and we just sort of focus on H plus interactions or H plus OH minus interactions. Okay, and since this is so dilute, it's just ideal. It's just like an ideal gas. So we've just renormalized everything. And for our simplicity of treating things mathematically, we just allow everything to be ideal. And so gammas for these kinds of systems are now allowed to be 1, okay, as an approximation. Now, if you have some very concentrated acidic systems where you can't neglect this, now the gammas become important and more relevant. Okay? But this is why you haven't seen these guys in the systems that you've been dealing with. Or perhaps some of you have. Maybe you noticed that sometimes your predictions of OH plus concentration or H plus concentration in your labs did not quite match what you measured, okay, or calculated. In fact, what you measured versus calculated. And it's really because of non-ideality. You didn't take into account non-ideality in your calculation. Of course, what you measure is what you measure. Okay, that's something that is real. Okay, and so now, the other thing to keep in mind here is that the other approximation was that all of these reference concentrations were taken to be 1 molar, okay? And that was implicit in this approach, or sometimes what you were told is that we'll just lump it in with the K and then we'll let that be another K, okay? So oftentimes H3O plus has been approximated in the reference state OH minus and H2O as 1 molar. Okay, so you approximate this reference state concentration as 1 molar, okay, and then that disappears, or it appears to disappear, but in fact it's really there. Okay. Any questions on that? Okay, so that's essentially how we would deal with this. The other way, when we talk about activities, in this case, you can say that, all right, well, on the left-hand side, we only have pure water. Another convention is that for pure species, or if you have something that's pure more or less, or in abundance, for pure species, was things that are not mixed, A sub I is taken to be 1. Okay, so we don't have to worry about their activities in solution. Okay. So any questions on that? Okay, great. So a corollary to this. Can someone remind me what pH is? Does anyone remember what pH, what is the definition, how one might take the pH is?
The negative log of the H plus concentration.
Okay, or H3O plus, yeah, we can use H plus, H3O plus, right? But when you see this, what strikes you as a problematic in this equation?
Log of concentration. There's a unit in there.
Yeah, exactly, right, Khalil? Exactly, right? So when you think, and this is why mathematics is often important, is that when you understand that you can't take the log of something with dimensions, it should start causing you some concern. But now we actually know what's going on here, right? Because in all these cases, what we have done, if you go back to this expression, right, naively, initially from Gen Chem or other courses that you've had so far, you use concentration, but what we see now is that there's 2 additions you have to make here. You have to make the addition of a activity coefficient, and you have to make the addition of a reference state concentration. Okay. And when you do that, what you're really getting is an activity, right? So really for this, you need to have H plus divided by the reference state, plus you need to have gamma of H plus. Okay, that's what we learned here in the above discussion. So in fact, this is what really is the driving or the relevant combination of things to consider. And of course, that's what this combination of gamma times this ratio of concentrations for H plus is just its so this guy is really just the what of hydrogen H plus. What is that thing called? Say it, say it.
Activity?
Exactly. So in fact, when you write it this way and you understand now what activity is as a measure of non-ideality and how it can allow you to extract the ideal case as a very specific case of something very general, we see that pH is equal to really the minus log of the activity of the proton or the H3O plus. And so once we understand that, everything is clear now, right? That pH has no units. No one ever told you that pH had to have units. And of course, it makes sense because the log of something cannot have units and activity does not have units because it's all normalized by either concentrations or a reference concentration, and the activity coefficient gamma is unitless. Okay, and so this is the most general way to write the pH, which is the minus log of the activity coefficient of whatever species that you're interested in. There's also a POH. POH would just be the activity of OH minus. Okay. So those are the more advanced and you know, thermodynamically, those are the rigorous ways to look at pH and chemical equilibria. Now let's take a look at another example where we have a solid, okay? And this is really just to address this idea of convention. So our last example here, what I want to discuss with you is, let's say we have calcium carbonate solid, okay, and we put this in solution or in water, we can have calcium oxide solid plus CO2 gas. Okay, sorry, not in water. We just have this equilibrium between the solid phase and the vapor phase. Okay, so we have three species, this guy, and this guy. Okay, they're in equilibrium as indicated by this forward and backward arrow. And by convention, which is this convention I've discussed above, what you're really seeing here in your reaction vessel, right, at equilibrium, is you're going to have a solid. Here's this little bit of solid, let's say just as a caricature, it's a cartoon. So this could be CaCO3 in the solid form. And over here, you might have a bigger lump, I don't know, of CaO, which is in the solid phase. And then all above, okay, you have CO2 in the gas phase, okay? So here what we're going to say is that for the solid, okay, it's really not a mixture, okay? We're going to take the activity of CaCO3 solid equal to 1, and we're going to take the activity of Ca oxide solid equal to 1 by convention. Okay, we'll just let those things, because you can tell that they're pure, okay? And so we don't, they're just some solid. We don't really have to worry about their ideality because they just exist as themselves. So remember this mixture, we don't have to worry about that. Okay, it's just a solid. Okay, now if we were looking at, let's say, a binary complex of CaCO3 and CaO, let's say there was some a mixed solid, we would have to then worry about it. Okay, but at this point, it's just calcium carbonate and calcium oxide. We don't, they're in their pure form that are just there in the system, and above them is this vapor. So we don't have to worry about that. The only thing we have to worry about is the CO2, and it's a gas. And so the only thing that's not equal to 1 is going to be the activity of CO2 gas, which would not equal 1 here. It would be either 1 or greater, greater than 1 or less than 1, depending on the pressure you're interested in. If it's at a high pressure, then you would have to deal with non-ideality. Okay, so this then would just be gamma I, gamma of CO2 in the gas phase. Okay, and then we can sort of say that, all right, well, what is CO2 over CO2 in some reference? And of course, we're going to have pure CO2, but we'll have some concentration of CO2 that we can use here. Or you can reformulate the CO2 if you consider it an ideal gas as a partial pressure or the pressure of CO2 above of the system. Okay, because if you treat this as an ideal gas, you know that you can always get concentration for an ideal gas in terms of the pressure of the gas. Okay, great. Any questions on that? So this is a way sort of to introduce you and sort of give you a few examples of how activity and activity coefficients arise in the physical quantities that you've seen before without the presence of activity and activity coefficients. Okay, so any questions? Was that clear or no? The importance of activity and how it's a very general quantity.
It was clear.
Okay, so actually at this point I'm going to call it a day for this course this semester. I think we've done a lot. I certainly hope that people appreciate thermodynamics a little bit more, and the fact that it is actually it is considered one of the 3 pillars of modern science. There's classical physics and classical mechanics, which embodies all things from electrostatics, electrodynamics, the statics, and, pulleys, all of that. And then there's quantum mechanics, and then there's thermodynamics. And so there's no hierarchy there. They're all the 3 pillars of modern science and engineering. And so, though maybe the other 2, or perhaps quantum mechanics has this aura of being exotic and I don't know what word it is. All of these 3 areas of science, in fact, are very fundamental to anything. And this is something you might know, right? When you even talk about biological systems or biochemical systems, you always invoke the terminology and the language of thermodynamics. There's always something there that you're dealing with, which is thermodynamic. So I hope that was, you obtained something from this course. And the other thing I hope is that you start looking under the hood a little bit more. And whether you choose to stay in science or engineering, that's up to you. But always in other aspects of your journey, whether professional or otherwise, always look under the hood. That's fun. First and foremost, it's always fun looking under the hood, and the rewards you get far outweigh any effort that you may put into looking under the hood. And I've been around for 5+ decades, so I think I've enjoyed those decades doing that and following that approach. Anyway, so I'll see some of you next semester in 444. I open the final bit of this time we have to any of your comments that you may wish to say, or any questions from the whole course that you may have, or anything you want to say regarding the course or anything. Sorry.
I have a question about the final.
Yes.
Will it be cumulative?
Yeah, it will be. But there's really going to be very little from this last little bit, as you can tell. So there'll be everything.
Okay,
I have a question.
Yes.
Do we have sample for final?
I can put one on Canvas.
Yeah, that will be helpful. Thank you.
Okay, but again, I don't guarantee that any of the problems on the exam that is practice would be the same. I always have to put that qualifier in.
I have a quick question.
Yes.
Do we have class on Friday?
No, I think the 10th is the last day
All right.
of classes. The other thing is that there will be no discussion sessions today. The TA will email you for a review session on Monday. For some reason, there's some conflict in his schedule. So I don't know whether he's sent out an email or not yet. So just to be aware of that. And I'm also available over the weekend. Just if you have any questions, as the day comes along, my responses may be a little bit scattered just because if I have many different people asking me questions, I can't answer them if I'm doing some other things. So just be aware of that. If you have any questions, get them answered earlier, better than later.
I don't think you ever posted the first midterm key.
Okay,
Should post that.
I will do that. I think everyone did well on that exam, actually. If you did well, I think, but I will post it, but, I think that was pretty high scoring exam. Okay, so, is everyone happy with the course? Did you get something out of it? I hope. Yes? No?
Yeah.
Did? Okay.
Yeah.
Yeah, definitely.
Good, good. So let me just remind people, this semester I kind of, I just because of COVID and everything else, I kind of decided that I would focus on quality, and I hope it was quality for you. This course I could have easily doubled the content and whizzed through it. But I really hope that people will appreciate, I did make an effort to make it a little bit more accessible and digestible. Just a little bit of a heads up that next semester will be, a much more rapid pace. And this is not to scare you or to, this is not a threat. It's just that because of the nature of the curriculum, it's going to be really, really heavy and intense. And so I just want to be upfront and honest about what your expectations should be for the course. It will be a little bit more fast paced than what was this semester. Okay. Just so you know. And, if you're welcome to read ahead, there will be electronic version of the text. You can, if you have the hard copy or the electronic copy, you can get those chapters and start reading. There's nothing wrong with that. And just stay ahead of the curve. Okay. Okay, any questions? It was a pleasure for me. I enjoyed the interactions, and people were catching me on my mistakes, so that was good. So I really wish this could have been in person. I really do. But all right, I'll stop talking. All right, I'll be in touch, and I wish you all the best on your finals and over the break, and wish you good health and be safe, everyone. Okay.
Thank you.
Thank you.
Thank you.
Thank you.
all.
Thank you.
Weekend.
Okay.
Thank you.